Okay, so good morning. Good afternoon, everyone. So today we are going to talk about optimization. So in today's session, I will just give you a brief introduction. We will just have a brief introduction about what is optimization, and then we are going to see what are the types of optimization. And if we get time, then we will talk about those types today as well. Okay, optimization. So let me ask you the basic question. What do you mean by optimization? You have seen this in your junior college, I think. What do you mean by optimization?
Trying to achieve a best possible outcome.
Perfect. Yes, very good. Any other answers? Okay. So it has derived from the word optimal. The meaning of optimal means the best. Okay. So whenever you go in a corporate, in a company, obviously you will have a problem or you will have some resources. Okay. So you will have some resource or you have some problem, and your job is to your job is to utilize that resource efficiently or optimally. Similarly, you have to solve that problem optimally, then only it is of use. Okay, so optimization is a process of making the best use of a resource. Okay, so it's a process of making the best use of the resource or a problem, of making the best use. Spare me for my handwriting, but I hope it's readable. If anything is not readable, you can let me know. So best use of a resource or situation. Okay, so you might have a problem. For that problem, you may have more than one solutions. But then what is the optimal solution? That is what my interest is. Okay, so for example, if you are starting a startup, okay, if you have your own startup, obviously what will be the main thing? The main thing is to get the funds. So obviously your job is to get the maximum funds. So that is a problem, which is a maximization type problem, because you want to maximize your funds. If you have a company, a well established company, obviously your main aim will be to earn the profit for the company, and that to not earn the profit, to earn the maximum profit. So that's again a classical case of an optimization problem. Or suppose if you say you are owning a transport company, you want to transport the goods. So obviously your job will be to minimize the cost of transportation of good. Okay, so all these problems comes under optimization. So whenever you have a problem which you want to optimize, obviously there will be some constraints. Obviously there will be some constraints which one has to look for. So like for example, if you want to minimize the cost of transportation of goods, you should, the constraints are like you should use the less amount of petrol. You should make sure what is the best route you should choose so that the oil which you're using will be used less. What should be the maximum weight I can put on the truck so that it will carry that much of the good. It should not be overloaded as well. So like this, there are plenty of constraints whenever you want to solve a problem. Okay, so therefore whenever you see a problem in optimization, it will always consist of a function and the constraint. Okay, so question is, how does an optimization problem look like? I hope I'm audible properly. Am I audible properly?
Yes, sir. Yes.
Yes, sir. Okay, good. So how does an optimization problem looks like? That is what the question is. So you will have a function f of x bar. You have a function in one variable, two variable, three variable, and you either need to minimize the function or you need to maximize the function. Okay, subject to what? Subject to the constraints. You might be having some constraint. So some functions, say gi of x bar, some less equal 0. Okay, where I is from 1 to n. So this is how, so there are some n number of constraints, and f is the function which you want to maximize or minimize, or f is the function which you need to optimize. So this is how in general an optimization problem looks like. What is my f? f is a function from Rn to R, and all your GIs are also the functions from Rn to R. Okay, your GIs are called as constrained functions. Your f is called as an objective function. I think you must have seen LPP in your 12th standard, right? So like it's kind of the same thing, but then instead of only looking at LPP, we will look at NLP as well. Okay, so your f, the optimal function, is always called as an objective function. Your GIs are called as a constraint functions. Okay, and your x bar, so it's a vector. We always write vector as a column vector, x1 to xn. These are called as a decision variable or a decision vector. Decision variable. I mean, you will come across these phrases a lot. That's why I'm just safer side. I'm telling you the phrases. So f is called as an objective functions. GIs are called as your constraint functions, and your x bar are called as the decision variables or the decision vectors. Okay, so that is one thing. Regarding these GIs, I have written less equals 0. You may have somewhere where GIs are greater equals 0. But then see, you can always multiply it by minus sign and you can make it less equals 0. Okay, so suppose you have a constraint 2x plus 3y plus 4z greater equals 0. You multiply by minus sign. You have minus 2x minus 3y minus 4z less equals 0. So you can always write your constraint less equals 0. Okay, therefore people usually study this case only. Whenever they write an optimization problem, they write gi of x less equals 0. Okay, because you can always convert greater equal constraint to less equal constraint by multiplying by minus sign. Okay, so one observation: constraints, in constraints you will observe that GIs are always written less equal 0. Okay, because if it is greater than, you multiply by minus, it becomes less equal 0. Second observation, they write an optimization problem always as minimum of f of x. Okay, so they will say consider a problem minimum of f of x and your GIs are less equal 0. But then you might think that why we are not considering maximum of f of x. What do you think? Will only considering minimum of f of x will solve my job? If I want to solve maximum of f of x, how will I solve that problem? Is the question clear what I'm saying? When you see a problem, they will write minimize f of x and your constraints are gi of x is less equal 0. You will hardly see any book which is saying maximize f of x. At least in theory, in problem you will have maximize. But in theory, usually people will write minimize of f of x and your GIs are less equal 0. The answer is, or my claim is, once you solve this case is also covered. Can you say how this case will be covered? Because maximize the function is same as to minimize which function? If at some point the function is having the maximum value, then for which function it will take the minimum value?
It's negative.
Negative. Perfect. So minimum of minus f of x. So if I want to solve this problem, I will call minus f as g, or say h of x. So you solve minimum of h of x. You solve this problem where h is minus of f. Okay. So therefore people always write minimum of f of x in theory. Okay. Because if you have a problem on maximization, maximizing f of x is same as minimizing minus of f of x. Okay, so these are the two observations I would like to just stress that you might come across, because usually after the course ends or after the chapter ends, people start realizing, oh, why they have not taken the case GI greater than 0, or why they have not taken the case maximize of f of x. The answer is this. These are the reasons for which they have not taken those cases, because you can always convert your problem P. If P is my optimization problem, you can always convert into this form: minimization of f of x subject to gi of x less equal 0. You can always do that. So you will always see such kind of problem, and we will try to tackle. We will see when does the solution for this exist, for such kind of problem exist. Okay, so these are the things. Okay, so far so good. Can you just give me thumbs up if it is clear, or thumbs down if you, or if it's not clear, you can give me thumbs down. So far so good. Okay, I can see a couple of thumbs up. Okay, good. If you have any doubt, you can just put in the chat box, or you can unmute and let me know. Okay. So that is one thing. Second thing is there's something called as a feasible set. You must have seen this earlier, but just let me recall. Feasible set. What do you mean by feasible set? Let me denote by S. They are those decision variables such that they satisfies all the constraints. GIs of X bar less equal 0. Okay, so this set is called as a feasible set. Okay, those vectors which satisfies all the constraints. It satisfies all the constraints. Such a set is called as a feasible set. Okay, and if X bar is an element of S, then we call X bar as a feasible point. Feasible point. Okay, and if X bar is in S and this point is optimizing your function, this point is optimizing your function. Optimizing your function means either maximum value or minimum value. Then such point is called as an optimal point. Then X bar is called as an optimal point. So you might see such phrases when you read some books, that X bar be an optimal point. That means what? At X bar, your objective is being achieved. That means whether it is maximum or minimum, it is achieved at this X bar. If they are writing let X bar be a feasible point, that means it is satisfying all the constraints. Okay, so this is the definition of an optimal point and the feasible point and the feasible set. Okay, so that's all about optimization, the basic thing, introduction. So it's nothing but your job is to get the best solution out of any situation or resource. Then the question is, how does an optimization problem looks like? So answer is here. This is how an optimization problem looks like. And then what is my constraint? What is the objective function? What is the feasible point? What is the optimal point? So all these are the standard phrases that one uses in optimization problems. Okay, now there are two types of optimization problem. One is called as LPP, linear programming problem, and one is called as NLP, which is non-linear programming problem. Okay, so what is an LPP? Where your F and GIs all are linear functions. All are linear functions. Then such points are, then such problem is called as a LPP, linear programming problem. When you call a function to be a linear function, when do you call a function is a linear function? If I have a function f of x, let's play with one variable. When I will call this is a linear function? Or can
f
you
of
give me an
mx
example?
is equal to mf of x.
F of x is equal to?
If f of mx is equal to f of mx is equal to mf of x.
Okay, so if f of, okay, so in that language, let me write it down. So if your f of mx is equal to m times f of x, then it's a linear function. Okay, good. So if you have two variables, then also the same thing. Okay, so if you have f of x is equal to x plus 1, then this is not the linear. Okay, so all the terms should have the variable and all of them should have the degree 1. Then such a function is called as a linear function. So when your f is a linear function and your all our constraints are also linear, then such a problem is called as a linear programming problem. Okay, and non-linear means what? If f or g or any of the GIs, if f or any of the GIs are non-linear or is non-linear. Okay, even if one of them is non-linear, that means degree is bigger than degree is not 1. That means f of mx is not equal to m f of x. Then such problems are called as a non-linear programming problem. Okay, and NLP are very difficult to solve. LPP is not difficult to solve. That's why in 12th or in your junior college you first study LPP because they're very easy to solve. Okay, so when both f and gi is all are linear, then LPP. If either f or gi or both are non-linear, then it is a type of an non-linear programming problem. Okay, so for example, if I write maximization of suppose z is equal to 7x1 plus 3y1 minus not y1, let me write x1 x2 x3 3x2 minus 17x3. This is the function which I want to maximize, and subject to I have x1 plus 2x2 minus 3x3 less equal 1 and 4x2 plus 5x3 less equal 4, and all my xi's are greater equal 0. Okay, so for I equal to 1 to 3. So this is an example of a linear programming problem. Okay, now and you can write this in a very much nicer way. How can I write this as? I can write this as max of z is equal to C transpose X subject to A into X bar is less equal B and your X bar is greater equal 0 bar. Can you just think for a moment and can you tell me what will be my C vector and what will be my A vector, A matrix, what will be B vector and what is my X vector? What will be my C vector? Any wild guess?
7, 3 minus 17.
Perfect. So you can observe, you can write this as 7, 3 minus 17 and you multiply by x1, x2, x3. So if you multiply this two, then you get the given function Z. So my C is a row vector 7, 3 and minus 17. Now these two constraint you can write in a matrix form. Okay, so how will you write? 1, 2, minus 3, 0, 4, 5. And here you have a column vector x1, x2, x3 less equal 1, 4. So your A matrix is nothing but 1, 0, 2, 4, minus 3, 5. Your B vector is nothing but 1, 4. And your X vector is nothing but x1, x2, and x3. Okay, so you can always introduce these vectors C bar, A matrix, B bar, and X bar. Okay, so people, this is a good, nice, and concise way of writing LPP as compared to the what I've written at the top in blue color. Okay, so that is one thing. Now see, whenever see you have studied convex functions, right? When you call a function to be a convex function, can anyone recall what do you, when you say a function f is a convex function? Or geometrical, no need to tell me the precise definition, even the geometrical idea is okay.
Line segment joining any two point of S in also in S, then it's convex function.
Okay, so if I draw the graph of this, suppose this is a graph of some function, is this function convex function? Yes, because if you take any 2 points on the graph, the segment joining the graph is above the graph. Okay, you take any 2 points on the graph, the segment joining the graph is above the graph. Okay, so such function is called as a convex function. Or the proper definition is if f of lambda x plus 1 minus lambda y is less equal lambda times f of x plus 1 minus lambda times f of y, then such functions are called as the convex functions. Okay, and convex functions are very good functions to play with. And then you have studied convex set as well. When you call a set to be a convex set, is this a convex set? This is a set. Is this set a convex set?
No, sir.
A set is said to be convex? No, because if you take any 2 points in the set, then the line segment joining those 2 points should be within the set. This should be true for every points, but this is not becoming true for every points, because if I take these 2 points, the segment is going outside the set. This is not a convex set. Okay, so if your x and y is in S, then the segment joining lambda x plus 1 minus lambda y should be in S, where lambda is between 0 to 1. Okay, now why I'm talking about this convex set suddenly in between, because if you recall your junior college ka LPP, linear programming problem, like suppose if you have whatever z is equal to 2x plus 3y, which you want to maximize, and if I give you suppose x1 plus x2 less equal 1 and x1 and x2 are greater equal 0, is this an LPP? Yes, because the function is linear, the constraints are also linear. If you try to draw the constraint, what is the constraint? x1 and x2 less equal 1. So this is x1 plus x2 equal to 1, and less means this one, and it is the first quadrant. Is this set a convex set? This is the feasible set. Is this feasible set a convex set? What do you say? By looking at the diagram, what do you think? If you take any 2 points, the segment joining those 2 points will again lie in the set.
Yes, sir.
Yes. Okay. So this is a convex set, and actually one can prove that in LPP, the feasible sets means this set, the set which satisfies all the constraints. Feasible set is always a convex set. Feasible set is always convex set. Why so? Why so? Because what is LPP? In LPP, the constraints are linear functions. The constraints are linear functions. So if you, whenever you have the linear functions, then you look for the points which satisfies those linear constraints, then those set is always a convex set. Okay, or in general, if you have the constraints which are convex, like linear functions are always convex. Okay, linear functions, you can try to prove it using definition. Linear functions are always convex. They are concave as well. They're convex and concave both, but only I'm interested in convex as of now. Okay, and since you have LPP, that means your constraints are linear functions and therefore they are convex. Then if you look at the points which satisfies those constraints, then that set is always a convex set. Okay, so set those points satisfying all linear constraints, or you can say convex constraints, then this set is a convex set. Okay, just homework. If you're not comfortable with this, just try to prove this. If you get stuck, you can ask me tomorrow. Okay, therefore, I don't know, you must have seen this statement somewhere in your 12th that in LPP, feasible set is always convex. And what is the plus point when you're having a convex set? The plus point is the extreme values, that means the maxima or minima, is always attained at the corner points. Just if you recall your 12th class, suppose if I say this is the, if this is the visible set. You can see this is a convex. If I call this as O, A, B, and C, if you remember, you always find these points O, A, B, C, and then you see whether the function is having the maximum or the minimum value. Can you remember this? Can you just give me a thumbs up if you remember these things which you have done in 12th? Okay, good. So I can see some people remember. So these are the basic things. So I'm just recalling a bit 12th. I'm not doing anything new. Okay. So such kind of things. So this is a convex set, and whenever you have a convex set, the optimal value occurs at the corner points. Occurs at corner points. That's why people are interested in convex functions or convex sets, because when you have convexity, things are nice. Things are very nice. Okay, this is for the bounded domain. If you have unbounded domain, then you may not have optimal value. For example, if suppose this is the convex region, and if I'm asking you what is the maximum value, then it does not exist. You can't say that it will exist at this corner point or this corner point. This is a maximization thing, and it's an unbounded region. So in this scenario, the optimal value is not occurring at the corner points. It's a convex set, but because since it's maximization problem, therefore optimal value is not occurring at the corner points. But when you have this bounded domain, then the optimal value, we don't have a proof, but one can always have a optimal value at the corner points. And that's the reason people study convex sets and convex functions. Okay, so that's one of the motivation I wanted to give, that why you study convexity and all. Because in optimization, convex functions plays a very important role. Okay, and in LPP, when you're in a linear programming linear programming problem, your functions and the constraints are linear. Linear functions are always convex. Therefore, the feasible set is a convex set. And since it's a convex set, whenever you have the bounded domain, the optimal value will occur at the corner points. Okay, so things are pretty much smooth in LPP, but they are not smooth in NLP, because in NLP, the region may not be convex. For example, if I give you a function, suppose you want to minimize or maximize, whatever. You want to maximize or minimize a function 2x1 plus 3x2. Okay, subject to constraint, subject to, I'm giving you x1 comma x2 strictly less than 1, and your x1 and x2 are positive. What is this? Does anyone know what is x1 into x2 is equal to 1? What is the graph of this equation? This is my x2 axis, this is my x1 axis. If you don't like x1, x2, it is xy equal to 1 or y equal to 1 by x. Does anyone know what is this? At 1, 1, this is 1, 1. Okay, well, it's a hyperbola. Okay, it's in the first and the third quadrant, but our x's are positive, so it is in the first quadrant and it's less than 1. Strictly less than 1. Actually, whenever you have a strict sign, no, we always use the dotted representation. We always use the dotted representation. And less than 1. So therefore, this is the region. Is this a convex set? Is this region a convex set? This is the point 1, 1.
No, sir.
No, correct. Because if you take 2 points, suppose if I take this point over here and this point over here, and if you draw the segment, then the segment is outside the set. And you can see that this is not a linear function because the degree is 2, 1 and 1. So when you have a non-linear programming problem, NLP, the feasible set need not be a convex set, and therefore the problem becomes difficult to solve. Okay, so we will try to see when NLP is a convex problem. Okay, that we will come across very soon. And in NLP, that is the first example that it need not be convex. What is the first example? Feasible set need not be convex. And second point, in NLP, your optimal value need not occur at endpoint. Your optimal value need not occur at endpoint. I mean corner point, need not occur at corner point. Let's say, for example, if I want to minimize my function x square plus y square, and subject to constraint, I'm giving you x less equal 1, y less equal 1, x greater equal minus 1, y greater equal minus 1. Can you tell me what will be the region? Can you just guess what will be the region?
Square.
It's a square, correct. X equal to 1 is this line, x equal to minus 1 is this line, y equal to 1 is this line, and y equal to minus 1 is this line. And because of this less equal and greater equal, I have all these things. This is the region. Okay, now this is my feasible set. At which point your function will take the minimum value? By looking at the feasible set and the function, can you tell me at which point? Can you tell me x bar where your z will be minimum?
0, 0.
Correct. It's 0, 0 because x square plus y square. So the minimum value x square plus y square can take is 0, and that is occurring only at 0, 0. So z equal to 0 is the minimum value, and it is occurring here interior point P. Okay, so the things in NLP changes drastically. Your feasible set need not be a convex set. The optimal point need not occur at the corner points. Okay, so therefore one has to be a little bit cautious while solving NLP, non-linear programming problems. Okay, so yeah, this is the categorization of a optimization problem, LPP and NLP. Now there is actually one more separate categorization which they call as IPP. Okay, broadly we say there are two classification, LPP and NLP, but IPP is also one of the classification which is called as an integer programming problem. So that means what? When all the constraints, when all your variables are integers. So when all the involved variables are integers, then such a problem is called as an integer programming problem. Okay, so this is also one of the classifications some author do, but broadly there are two, LPP and NLP. Okay, some people also write IPP, so I just thought of telling you. Okay, so when all the variables involved are integers, then we call it as an integer programming problem. Okay, now another classification of an optimization problem is optimization. We will do some examples later on, but let me just give you the idea of this. They are classified into unconstrained optimization problem, unconstrained optimization problem, and constrained optimization problem. And constrained optimization problem. Now, what do you mean by constrained and unconstrained optimization problem? So let us try to see and let us try to understand that. Now, suppose you have a problem. You have a problem P. You want to minimize the function f of x bar subject to the constraints gi of x bar less equal 0. Okay, what is my f? F is an objective function from Rn to R. Your gi's are the constraint functions from Rn to R. Okay, and this x bars, they are in Rn. Okay, your x bar is in Rn. Okay, now so let me call this as set let me rewrite this problem in another way. This one is this problem P, minimization of a function subject to the constraint. I can also write this problem in another way. What is another way? I have to minimize the function, and my C is a subset of Rn. Where what is my C? C is my constrained set. C is my constraint set. Okay, so what is C? those x bar in Rn which satisfies GIs. Okay, so either you can write down the problem in the language of a function GIs, or you look all x bar that is satisfying GIs, and I'm putting that x bar into C. Is the difference clear what I'm trying to say? The difference between the C and the GIs. GIs are the functions that you can write explicitly the constraints, or you look for those x bar, the feasible set. You can say that your C is the constraint set or the feasible set. C is those points in Rn which satisfies all the constraints. So this is my C. Okay, the constraint set. Okay, so when your this constraint set is complete Rn, then I will call the problem as an unconstrained. There is no constraint. It can be anything in Rn. Unconstrained optimization problem. And if your C is a proper subset of Rn, then you call this as an constrained optimization problem. Okay, that means when your C is Rn, that means it can be anything into Rn, means there is no restriction on C. Your C is complete Rn. So no restriction means unconstrained, no restriction. And when C is the proper subset of Rn, that means it should satisfy some conditions. That means we call it as a constrained optimization problem. Okay, so minimization of f of x bar subject to x bar belongs to C. What is my C? C is called as a constraint set. If the constraint set is complete Rn, we call it as an unconstrained optimization problem. If it is a subset of Rn, we call it as a constrained optimization problem. So example, suppose if I say f of xy is equal to x square plus xy plus y cube minus 3x square y something, and I want to minimize this function. And if I say my xy is in R2, okay, because for every xy I have an output, so I'm taking my domain as complete R2. So this problem is an example of an unconstrained optimization problem. Unconstrained optimization problem, because I want to find the minimum value of the function, and my x comma y can be anything in R2. So there is no restriction on R2. Suppose if I take the same function, minimization of f of xy, suppose I'm taking the function x square plus xy plus y cube minus 3x square y, and I'm saying my xy should satisfy the equation subject to x square plus y square less equal 1. So what are the points now? They are the points on the circle and inside the circle. Unit circle. Now here there is no freedom on xy. Xy cannot be anything in R2. It should be lie within the circle or on the circle. Okay, so this is the constraint. So therefore, this is an example of a constrained optimization problem. Okay, so in the second example, the first example, I have to minimize the function, and xy can be anything from R2. Therefore, it's unconstrained. In second problem, I have to minimize the function, but my restriction is I have to look for only those points which are inside the circle or on the circle of radius less equal 1. Is the difference clear between the unconstrained and the constrained optimization problem? Thumbs up if yes, thumbs down if no. Is the speed okay? Am I going very fast? Ashu, how is the speed? Is it okay? Vinay?
Yes, sir.
Okay.
Sir,
Aman,
I'm
Pradnya? Yes.
yes, sir.
Yes,
I am
sir.
comfortable.
Okay, okay, fine. Okay, okay. Vinay, Sakshi, is the speed okay?
So I would like to, can I just have these class notes that you are writing in class after?
Yes, yes, I will
in a
upload the
separate form?
lecture. I will share the PDF, everything I will do. That's not a concern. So don't worry about writing the things. Okay,
So
don't
that
worry
was the
about
point. I was
Okay.
missing few things here and there.
Okay,
So I
no,
just
don't
wanted.
worry about writing down the things. I will share the recording of the lecture, and I will also share the PDF of this, whatever I'm writing. Okay, so make sure the concept is clear.
Okay, sir. Thank you.
Okay. Okay. Vishal, Sakshi, any comment? Pradnya, or it's clear?
Yes, sir, it's clear.
Okay. Okay, good. So that is the thing. So first we will talk about unconstrained optimization problem, and then we will talk about constrained optimization problem. Constrained may one has to spend some time. Unconstrained is, I think you might have seen this. You have seen the concept of local maxima, local minima, absolute maxima, absolute minima, Hessian matrix. You have seen that, right?
Yes, sir.
In
Yes,
earlier
sir,
lectures. Yes. Yes.
Yes,
So
sir.
there's the same thing here as well. So I will just briefly recall unconstrained optimization problem, and tomorrow we will talk about constrained optimization problem. Okay, so today let me give you the brief idea about the constrained optimization problem. Okay. So how does the problem look like? Minimum of f of x bar, and your x bar belongs to Rn. This is how the problem looks like. Okay, so question is, if it is maximum, then how to find? Question is how to find point of local minima or global minima. And if it is a maximization problem, then how to find the point of local maxima or global maximum. Okay, so those things you have seen. So there's a theorem, I think that's also you must have seen for two variable case. Let me talk that for in general for n variable case. Okay, that is called as optimality condition. Optimality condition. So if you have a function from U to R, where U is a subset of Rn, okay, and suppose your x bar is an interior point of the set U. It is an interior point, not on the boundary. Okay, and suppose x bar is a local minima or local maxima, is a point of local minima or local maxima, and all partial derivatives of f exist. So if my x bar is x1, x2 up to xn, that means dA by f by dA by x1 exists, dA by f by dA by x2 exists, up to dA by f by dA by xn also exist. So if the all partial derivative exists, then the partial derivatives at this x bar, all of them should be 0. Do you know what is this notation? Nabla? What is this?
Gradient.
Gradient of f, correct. So gradient of a function is a vector. Gradient of a function is a vector consisting of partial derivatives. That means what I'm saying is grad f at x bar is 0 means what? What is this? You differentiate f with respect to x1 at point x bar, f with respect to x2 at point x bar, f with respect to xn at point x bar. This is a 0 vector, means each of them should be 0. Okay, I think you must have seen for two variable case. Okay, if f with respect to x is 0 and f with respect to y should be 0. Now I'm talking about in general. So if you have a point which is an interior point, and if at those points the partial exist, and that point is an optimal point, matlab that point you are having either maxima or minima, then the partial has to be 0. You don't have any choice. Okay. And another definition is a critical point. Have you seen the definition of critical point? Or sometimes also called as a stationary point. Okay, so if your x bar is a point of an interior of a region, not the boundary point, and f is a differentiable at x bar, f is differentiable at x bar, and if the grad f at x bar is 0 or not defined, let's say 0 is 0, then we call x bar to be the critical point or the stationary point. Okay, so whenever you want to find the maxima or minima, you first find the critical point. How do you find the critical point? By taking the gradient to be 0. Okay, and then once we have those points, how do we determine whether that point is a maxima or minima? Then we take the help of the Hessian matrix. Does anyone know what is an Hessian matrix? It's a matrix consisting of second order partial derivatives. It's a matrix consisting of second order partial derivatives. If you have a function in two variable, how does the Hessian looks like? I think this in the last lecture you must have seen this.
fxx, fxy,
Yes, correct.
fyx,
fxx,
fyy.
correct. fxy, fyx, fyy. If you have a function in three variables, then how do you define the Hessian of f? fxx, fxy, and fxz. Then go for y, fyx, fyy, fyz. And go for the third one, fzx, fzy, fzz. And so on. If you have a function in four variables, you will have a Hessian, a matrix of order 4 cross 4. So this is what the Hessian is defined. And once you have this matrix, how do you say whether it's a local maxima or local minima? So let me take the scenario for 2, f of xy. If all principal minors are greater or equal 0, then x bar is local minima. If principal minors are negative, positive, and so on, then x bar is a point of local maxima. Okay, so let me just briefly recall whatever we did till now. So we are seeing how to solve an unconstrained optimization problem. So whenever you have a function in n variables, you first find the critical point. How do you find the critical point? You take the gradient, you equate it to 0. Okay, actually we are assuming function to be differentiable. If it's not differentiable, then you look for the point where the gradient is 0 or the gradient is not defined. Once you have the critical point, you use this Hessian matrix to determine whether that point is a point of local maxima or the local minima. Okay, so for example, if I want to take an example, just to make sure the picture is clear, if I have f of xy is equal to x square plus y square plus 2x minus 2y plus 4. Can you find the critical point for this? How do you find the critical point? You find the partial derivative equal to 0. You find the partial derivative with respect to x and y and equate them to 0. So you have 2x plus 2 equal to 0, and here you have 2y minus 2 equal to 0. So therefore your x is minus 1, your y is 1. Therefore the critical point is only 1 point. X comma y is equal to minus 1, 1. Now whether you have maxima or minima at this point, you take the help of the gradient, a Hessian matrix. So what is fxx? It is 2. What is fyy? It is 2. What is f of xy? 0. What is f of y with respect to x? 0. So what will be the Hessian matrix? Can anyone find the Hessian matrix and tell me? Okay, so let me write it down. So the Hessian matrix is nothing but 2, 0, 0, 2. What is the principal minor? Is the first entry. The first entry over here, which is positive. What is delta 2? The determinant of this first 2 cross 2, which is nothing but 4, which is also positive. Therefore, minus 1 comma 1 is the point of local minima. The point of local minima. Actually, I have done the recording of this topic separately as well. I will share that link with you as well. Okay, so that it will be easy for you to understand. There it has some more examples. Okay, so unconstrained is kind of very easy to solve. You simply find the stationary points, you take the help of the Hessian matrix, and you see whether it's a maximum or minimum. The problem arises for constraint optimization problem. And in real world, you always face the constraint. Okay, because it's never like you have one constraint. So you will have plenty of constraints whenever you model a problem. So therefore, constraint optimization problem is an important point that one should understand. And that we will discuss tomorrow at 12:30. Okay, so any doubt for today's session? Or if you want, you can go through it and you can ask me tomorrow or on Monday, not an issue. Okay, so I will share the PDF and the recording link with Ashu, and Ashu will then share with you all.
Yes, sir.
Okay.
Yeah.
Okay, so thank you everyone. It was nice
Thank you,
meeting
sir.
Chalo, take care. Bye bye.
Thank you, sir.
Thank you.
Thank you, sir.